probably 5 years.
Four panels,
Yeah, that's easy to
watts,
replace.
Right.
equals less than a kilowatt system.
And here's the cold water comes in here, this line here. Cold water comes in, and the hot water comes out here. And this valve is closed, so the cold water is forced to go into the tank and then out here. Now, this is the summer bypass, where the water's coming out here and going up to the application, to the faucets, bypassing the tank. And when this is closed, and this is open, then the hot water comes over to the conventional tank. Right here,
So it can be
right there.
heated, higher temperature.
Yeah,
That's the drainback system?
this is a drain back system, yeah. Yeah, and we have done, as I mentioned, closed loop systems. In fact, this sodium tank could be used for a closed loop system. It's not open to the atmosphere. But if we could fill it up, so here's the sight glass, and we normally fill it up to about the middle of the sight glass. And then we typically turn it off with these little valves. And pardon me, when it's pumping, we're pumping, and the level will drop down to about here, the level in the tank, in the outer tank. And then when it runs back, it goes back up to where it was. But you can't measure the level in the tank when the pump's running. You have to wait until it has run back down.
Bob, in the long run, have the most problem for maintenance? Like the heat exchanger or the pump? Or
Probably,
keep your eyes
well, typically,
on?
maybe a sensor. There's a sensor, and I should have brought one. It's the size of a pencil, 1.5 inches long. And it goes one up on the collector and one on the tank. Actually, the one on the tank, there's a dip tube in here, and we insert the sensor, and it's down about here. So that's the temperature of the cold side, and that's the hot side, and this compares the two temperatures. And when the temperature is greater than 10 degrees, it turns the pump on. When the temperature difference drops to less than 4 degrees, it turns the pump off.
So what you're saying is the sensors are the things that tend to
Yes,
fail?
there might be a lightning strike. We're not sure. We find that there's a problem with a sensor, and we're generally not sure why it failed. The way they're made, they're very reliable, but occasionally we have a sensor goes unserviceable.
The good part is they're not expensive.
Yeah, yeah.
What's the failure rate of it?
Less than half a percent. No, one in 500. You mean of the systems or just the
Of the
sensors?
sensors.
One in 1,000.
What?
1 in 1,000.
Over how many years?
5 years, 10 years.
Okay.
Yeah. Like last year, we've sold maybe half a dozen sensors for people that have wanted them. And generally, when they buy one, they buy a second one as a spare. So we've sold maybe a dozen sensors in the last year. And people can identify the problem themselves usually. There's something, well, there's a readout here and a schematic of the system. And there's a flashing dot which indicates which sensor you're measuring the temperature of.
There's a power point,
And when it's faulty, there's an indication.
And that's not adjustable, it's preset at the factory.
Yeah, the temperature difference is settable.
So,
Yep, there's a number of functions that are settable.
so you can change between 4 and 10.
Oh, yeah,
You go
yep.
like 5 and 11.
Yes, yep, any ratio you want, or any specific numbers you want. Yep.
You mentioned lightning strikes.
Yes.
Being made out of metal, are these often hit by lightning? And
No, no. Well, it's all grounded, you know, this is fastened to a metal rack, but all the plumbing comes down to here, and we ground this to something in the house that, so it's not isolated.
But that's copper piping versus PEX tubing.
Yeah.
You wouldn't have any ground if you used PEX tubing. So, fairly simple.
Tim mentioned about the PEX piping. We had an experience with PEX piping. We had a system on New Tech on McCormick Boulevard. And well, up until that time, I was quite excited about using PEX because it was so easy to install. But the problem is that it softens as it gets warmer. And as it softens and under pressure, it just pushes apart. And the fluid leaks away. So you've had a catastrophe on you. But we also have used polybutylene piping on another job. In fact, I have a thermosiphon system model in my van. A thermosiphon system is a collector with a tank above it. I don't think Tim mentioned that. But thermosiphon system is good for cottages or areas or where you have potable water in the system and there's no danger of freezing. So a summer cottage where you're going to drain it at the end of the summer, or your villa in the Caribbean.
Is that the one that's used in China all the time?
Yeah.
There are a lot of thermosiphon systems.
And they're half the size of this. This is sort of a Hummer.
Well, we use this for our thermosiphon, but we did use a smaller collector, 34 by 76, which was in 75, after the first oil embargo, which some of you may remember. There was a big push in the US to install solar. And most of the solar collectors initially were 34 by 76 because they needed to use tempered glass, and the standard size of tempered glass was for patio doors, and they were 34 by 76 inches, that is, for people that don't remember that. So 34 by 76, and then they went to 46 by 76 and 46 by 84, 46 by 96, which this is. And now there's also 46 by 120. But this is the most common size now. But it all goes back to the size of patio doors.
And can I just ask, I'd like you to mention something about the bubble pump,
Okay.
which is an invention that's
Okay.
found in Ontario. But do we overcome the sensors if we use a bubble pump?
Yeah.
Overcome the which?
The use
Sensors.
of sensors.
Oh, yeah.
So can you possibly talk about that in your involvement with
The
it?
bubble pump is like a coffee percolator. You know, the coffee percolator, there's a little broken part at the bottom of the stem, and then you see bubbles coming out of the stem. Well, the bubbles of steam, water vapor, form in the stem, and they move up. They're lighter. The bubbles of vapor are lighter than the fluid around, so they move up initially slowly and more rapidly, and eventually they're going up so fast that they hit the top of the coffee pot, and that gives you, the typical sound of a coffee pot. Well, the bubble pump works in the same way, that it's hooked up to the top of the collector. The system has to be reduced in pressure down so that it'll boil at the atmospheric temperature, maybe say of 70 or 20 degrees C, and the pressure at that point is about a third of a PSI, where atmospheric pressure is 14.7 PSI. But the pressure is low enough so that when it gets warmer, up to say 70 Fahrenheit, bubbles of vapor form, and eventually they puff, puff, and as the fluid goes up, it drags fluid behind it, and it's connected to a tank in the basement, and the bubbles flowing up drag the water from the tank up back into the collector, and so the loop is warming up in the collector, going into the bubble pump, down to the tank, and back up. And Will Sorensen, an architect in London, in Kingston, developed this. And he was a successful architect, but he got the solar bug, like a lot of us do, and devoted his time and his savings into developing this product. So now he's no longer an architect, and I think he blew all his money. He keeps trying to developed this product. Now, Energy Mines and Resources, which was the forerunner of Enercan, Natural Resources Canada, spent well over $100,000 on this product, but they didn't give it to the inventor. They gave it to a company out in Vancouver, Solar Systems, to commercialize this product. Well, they didn't commercialize it. They did a whole lot of testing. So what Wilf, after Solar Systems went out of business, Wilf got all the test results. So he's got boxes and boxes of test results. And then there was a little bit more money that went to Queen's University, and they did some more testing, and it came time to put 2 of our panels with the bubble pump on a job in Kingston, and Wilf was wanting to use these test results. He found that Queen's had tested the system with ethylene glycol rather than propylene glycol. Ethylene glycol is what you use in your car. Propylene glycol is what we use, but it has slightly different characteristics. So he keeps trying.
But the beautiful thing about the bubble pump, if you connect it, you know, you have another inventor here of the system. The two have worked together with the bubble pump, and I have seen your system work with the bubble pump.
Yeah.
The nice thing about it is that it's fully autonomous. You
Yeah.
don't need any
You look up on the
electricity.
roof, and you can see, when it's percolating, you can see the bubbles moving up.
Yeah.
And so you can identify or know that the system is working. Now recently,
So that
2 years,
replaces the pump is what you're saying?
the pump is
The
working.
bubble pump, or?
Yeah.
So the bubble
The
pump
bubble
doesn't
pump,
need any
yeah,
electricity
yeah.
at all,
That's right, no electricity, yeah. And,
if it works.
Oh, it works all
well,
right.
yeah, okay, there's a campground just north of Kingston, Rideau Campground. And Wilf, he bought the 20 panels from us and installed 2 bubble pumps. And each bubble pump is about a diameter like this, so each one is running on 10 panels. And it has a little cupola on top. It's a neat looking thing. I don't think I have any pictures though, but you can see the bubbles. And there's an array over here with, well, maybe it's the top array, 5 here and 5 here with a bubble pump, and 5 here and 5 here with another bubble pump. And so they may not be both working at the same time. Oh, yes, you had a question.
How critical is the angle of the panel? I mean, could you
No.
mount it on a vertical wall?
You
or-
could, yeah,
Yeah,
yeah.
it's not like the photo
The
cell.
best angle generally is equal to the latitude. And we're at 43 degrees north, so we typically set the panels at 45. However, we were setting PV panels when we installed them. We were installing them at 45, but we've since found that they work better at 35. They work later into the day. This will reach its maximum temperature about 2:30, 3:30 in the afternoon. And then the intensity of the sun is less as the sun gets further west, and there's more atmosphere for the sun to go through. So the intensity of the radiation is less. And the water is probably at its maximum temperature by 3 o'clock. So after that time, we're not getting useful energy. But for a PV module, where there's a continual demand or use of electricity, then it might work till 5 o'clock in the afternoon, 5:30.
The optimal angle also varies winter versus summer.
Yeah.
So if your goal is to collect energy in the wintertime, you're going to want to go up to about 60 degrees. In the summertime, typically 30 degrees, and that's hence where you end up somewhere in between the two at about 45, which is sort of an average all year round type of thing. But it depends on what you're aiming to do. I mean, if you're a school or something like that, and school's out in the summer, you don't need any hot water in the summer, so you might want to go with a steeper angle type of thing during those periods of time.
Yep. Now we have had variable tilt panels on a fixed roof. There's one up near Wingham that we did, and it's difficult to be able to vary the tilt. It's not like wiring where you can easily, the wire flexes, but we installed silicone rubber hose to make the connection where the piping was going to bend. And I tried to dissuade the customer from having that. It was going to cost him extra money. He said that was fine. He was wanting to do it that way. He called, well, that was at least 8 or 9 years ago. And he called us a year ago or so about his demand heater, tankless water heater. He wasn't able to find anybody to fix it. And I said, oh, by the way, how many times did you change the tilt on your system? Once, the first year. It meant getting up on the roof and having to move the two collectors simultaneously, and he just didn't do it. Sure.
Put it on a tracker.
Well, they're heavy, and they're typically bigger than the PV modules.
But you don't need as many as PV models.
That's true.
You know, like 2 or 3 of these panels on a small tracker system.
Generally speaking, instead of having a tracker, like the trackers sort of make sense in your head, but instead of having a tracker, an ultimate layout and ultimately the cost of repairs or maintenance down the road, it's just simpler to put another collector on if you're not getting enough energy. It's simpler, cheaper, easier, less problems, less headaches to worry about.
And the other thing is that the panel is most efficient when the sun is perpendicular to the surface.
Yeah.
And very seldom is the sun actually perpendicular. Only noon on the 21st of March and the 21st of September. And other times it's off a bit,
Yeah.
you know, as the sun's apparently going further south or further north. And if you track the sun from the east to the west, well, it's maybe 3 or 4 times the air mass between here and the sun in the morning than at noon.
Yeah.
And all that air mass absorbs the energy, so you get very little energy at 9 o'clock, 8 o'clock, say, 8 o'clock in the morning. You get less than you would at 10 o'clock and less than you would at noon.
But that said, would concave work better? No, the panels
No,
are...
no, it's still whatever's intercepted in that plane.
That wouldn't give you any added benefit of concave?
The benefit of concentrator, concave surface, would be higher temperature because you're focusing the energy from this area onto this area. So you get a higher temperature. But it's the same amount of energy that's intercepted by
There's no gain.
that area. Yeah. Yes.
To sort of counter the idea about would you adjust your panels or not, I helped build ecological houses in Ontario with some people, and it depends on your mindset if you want to take the time to do things like that. Like if it's only a couple times a year, we were actually moving our photovoltaic panels 4 to 6 times a day. Like we had them on a tracker and we're manually moving them. And what we'd be doing is you'd be building, you'd be working hard, helping on the house for an hour and a half, and then you'd want a stretch break, so you'd go over and check the panels.
Over there.
Wow.
Come over. If you wanted to watch movies that night after your day of work, you moved the panel. Otherwise, you work in the different. So it depends on how focused you are, whether you're willing to get up and do stuff. Yep. Oh, and it was an 8-panel system expanded to 10 while I was there. So it was, yeah, but it was actually pretty light. Once you get it moving, it actually, just by hand.
Gore has one of our solar systems.
But my question is about, because our house is east-west, the roof is east-west facing, and the panels we put on obviously the west side. But I was thinking of, many days there's a nice sun in the morning, but not in the afternoon. Would it make sense to also put one on the other side? And have you ever done systems where you try to utilize both the morning and the afternoon sun?
Gore's house is we put the 2 panels on a west-facing roof, and he's wondering if maybe we should have put one on the east-facing roof. But the plumbing would be more difficult, because you have to run the fluid to 2 panels and come back from 2 panels. I think overall it's better to either face west or east, and probably west because the atmosphere is warmer in the afternoon, so you can get higher temperatures.
There's very little justification for doing that. And like Bob says, the movement of the plumbing, the extra cost involved in the plumbing, it doesn't justify that.
And this computer simulation, we use computer simulations when we're not sure. a program that's available. It's RET Screen, R-E-T, standing for Renewable Energy Technology Screen. And it's available through the NRCan website. But we look at, it gives, you can calculate the solar radiation for a hot water load in various locations like London, Toronto, Ottawa. There's a number of, Mount Forest is another one, but there's information on this website so you can calculate for using the solar radiation and the weather data for a particular location. And it also shows the azimuth, whether you're facing directly south or 45 southeast or southwest or even east or west. And the efficiency of the system drops off about 15% if you're directly east or west. Which is a consideration, but it could be, it's easier to, or probably simpler to add another panel than it is to have the panels on both sides of the roof. Something else we've done, but we didn't on the Boras, is incline the panels to the roof surface. The Boras are flat to the roof, but we have installed them so that they're like this. There was a house on, what's the one north of Central?
Piccadilly?
Which? Oh, no. But maybe. No.
The one just north of Central.
Yeah, there's one north of Central.
The little strip.
Well, it doesn't matter. You know the one north. So, well, about the third house in, the fellow that lived there had a whole lot of apartments in that area.
Yeah.
And Bill McNeil. And he wanted solar on his own house, and the ridge ran north-south, so it was either east or west. But we built a rack at the north end of the house on a wooden frame, so they were in the plane facing south. And the house beside him, it was a two-story house, and we inclined those panels like this. So they were facing south, but inclined to the roof.
The glass.
Yes. Low iron?
No, the surface roughness in behind, why is it so rough?
There's a stippled surface on the underside of the glass. You can buy glass, tempered glass, that is also as smooth as this side, but this glass is made by rolling rather than float glass. And when it's rolled, it isn't even. And when we put it on the collector, we have to put weights on it to make it flat. And the stipple removes or obscures the imperfections in the glass.
So if it was...
And I've heard theories how it refracts the light and so on, but I think it's more aesthetic than it is utility.
If it was completely smooth, and would that allow more light in? Would you
I don't think so. The transmissivity is primarily a characteristic of a glass rather than the stippling. I think just maybe diffuses the light a little bit, but you're still going to get the same amount of light inside.
Yeah, it's mostly for aesthetics. I mean, part of it is so you don't see some of the stuff going actually underneath the glass there, the absorber strips or what have you, basically. So Bob's right. I mean, the glass itself, being a low iron glass, allows better transmission of the light through, essentially. And there's different, depending on the manufacturer, there's different patterns that you'll see underneath. One of the things that people have often, or sometimes people complain about, or at least in the past, Bob will probably know, is the appearance of the collectors. And I think part of the design has been to try and make collectors that look like skylights so they're not so obtrusive on people's buildings. And so they don't, look ugly. I mean, I don't think they look ugly to me, but then I'm in the solar business, right? So, but that's part of it.
When you hook up two, do you hook them up in series or parallel?
In parallel. There's a union on each corner. There's a header across the bottom, another header across the top, and there's one side of a union. And so that hooks onto that one, it's an opposite, there's one's male, one's female, and we hook them up. And we generally introduce the fluid, well, we always introduce the fluid at the bottom of the collector, and generally from the right-hand side. And so we have an end panel, which has the top header cut and capped inside the panel. And so we come in the bottom through the 8 risers, and then some of the fluid flows into the next panel and up those 8 risers, and into the next panel and up those 8 risers. And we typically connect 5 together in commercial systems.
How are the risers constructed?
It's a fin, about that wide, 5.5 inches wide, with a copper tube fastened to it, and the surface of the fin is selectively coated. It's either an anodizing process or an electroplating process or a paint that has characteristics. But the characteristics we want are high absorptivity, so it absorbs the maximum amount of light that comes in, and we want low emissivity, so it emits the least energy re-radiating back. And every surface re-radiates depending on its temperature. And as the characteristics of the glass is it allows the low frequency, low wavelength, glass in the visible spectrum lets it through, but in the spectrum where it's re-radiating back, the glass has a characteristic of low transmissivity, and so it traps the energy, and we call it the greenhouse effect.
Other manufacturers also manufacture a different type of collector slightly to what Bob has here. And what they use there is they actually use one solid sheet of material, either copper or aluminum. Generally it's referred to as your absorber plate. And instead of the individual strips that Bob has here in his design. And with that, as I showed you, you can either have a serpentine type of thing or you can have the straight risers. In either case, usually they're either laser welded or ultrasonically welded to the absorber plate, and they sit on the back side of the absorber plate that you can't see. And then at the bottom and at the top of the header pipes, they're generally brazed type of connection with the straight riser tubes. The serpentine tubes, the advantage of that is there are usually no internal connections in the collector itself. Having said that, a well-done brazed joint can be or is stronger than the tube itself, for bursting pressure. If the brazing is not done properly, then you have a potential source for leaks.
We made 30 years ago we were making serpentine panels, used an aluminum sheet with grooves formed in it, and then we used 60 feet rolls of 3/8 copper tubing, which we bent to go into the serpentine, and we fastened the copper to the aluminum with heat transfer cement, which is used in the petrochemical industry. And we installed 60 of those in a project in Kenya, in a university in the Rift Valley. And I've been wondering recently whether that system's still running. Many that we did at that time, or that we installed in Canada at that time, have been running, unless they've been neglected. There was one at the university that we did about 85? About 85, and which was removed from Thames Hall about 5 years ago because the university neglected to do routine maintenance, and that was one of the points that Tim made about maintenance. All they have to do is make sure that the system is full of fluid and that the controller and pumper is working. And people, if they neglect that, then it stops working.
Now your design here, it's like a waffle type. Does that maximize solar radiation?
You mean the waffle?
No, like there's 8 panels in there.
Oh, no.
Are they also going to be?
Okay, you can see the ribs, the tubes are these, appear to be lines. That's the tube in the middle of the fin.
Right. Yeah, what I'm saying, I guess that was, there's one section.
Yeah, that's right.
And it's V like that.
No, well, maybe it is, but it's not deliberate. It's more, that's the way it was manufactured, and by being V'd, it's a little more, has a little more strength to support itself. And also the waviness on the side, that corrugation stiffens the material. It work hardens it and stiffens it.